All right, so the first 6 questions are going over which tests are going to be used. So we've got this one. Says indicate which test should be used to determine whether the series below converges or diverges. So we've got that summation. And it's going to give you this. So this actually is all part of the problem. So it literally is going to say solution and give you a couple boxes to fill out for this problem. So that's actually the way this problem is going. So in this case, it's telling you a to the n. So it's asking you to do so remember this part right here, when they're saying an, they're talking about that part right there. So an is that. And we're saying an goes to, they're talking about the limit. So it's the limit as n goes to infinity of n minus 5 over 5n plus 5. So if we divide everything by n, this goes to 1 minus 5 over n, and then 5 plus 5 over n. So my limit as n goes to infinity of an goes to 1/5. So that's the number that they would expect in that box there is 1/5. So since the limit does not go to 0 in this situation, we're going to use the test for divergence. And actually in this one, since it does not equal 0, diverges. So it's 1/5 and the test for divergence would be the 2 answers to that question. That's how they're having you actually go through and do it out. Like a couple of things that I'm trying to test on this test is I want you to be able to actually tell me if it's convergent and divergent. But since those questions are literally a 50-50 shot, these questions are getting me to understand, do you actually understand which tests to choose and why you're choosing them? So that's the other part that I really want to make sure you understand. All right. Next one. And yes, they actually do say example 1, example 2, and stuff like that on the test. So it's just the way they made up these example problems. All right, so this one, same concept. We want to be able to figure out what information they gave me. And they do give you some help in there. So since a to n is an algebraic function of n, we compare the series given with a p series, the comparative series for, and then you have to select what you're doing with it. So you have a couple options. So if we're doing the comparison test, we have just the plain comparison test where we compare it to one or the other. But remember, those, when we're looking at those examples, I need to have, it would be very specific. So if my original function is less than bn and bn converges, an converges. If an is bigger than bn and bn diverges, then an diverges. But if we can't determine that, or if it's the other direction, then, so if we have an and bn and we can't tell what it is, then we have to do the limit comparison test.
Is bn just the one where it's just 1 after an, or like a plus 1? Is that it?
No, BN is what we're going to, so we're going to simplify down the problem to see what we're going to compare it to. That's what BN.
Okay.
So actually in this problem right here, we have, actually I'm going to double this one. So I keep that tab there. So move that. Keep those notes. All right, so in this case, remember the BN basically we're just looking at the biggest parts of the top and the bottom. So that's the square root of n to the third over 8n to the third. So and then they simplify it, they just break down the actual, that part there. And then they want you to finish simplifying it down. So in this case, it ends up being 1 over 8n to the 3 halves. So that's the what's going to go in that box there. Or you could also write it as 1 over 8, the square root of n to the third. You could write it that way too. Either one would work. So the thing about that we have to figure out is, so now this right here, that's a P series. So this is a P series where P is 3 over 2, which is greater than 1. So it converges. The question that we have in the problem, so since it converges, I need to show that the plus 5 over 8n to the third plus 6n squared plus 3 would be less than 8 that. And unfortunately, that's not easy to do because the top and the bottom both change. So since I can't easily determine this, the test that we would use for this one is the limit comparison test. And that way we don't have to determine if it's less than or greater than.
So the first step is a test or a procedure that we should know of? Is it
What?
also
This?
called, is it all just part of the limit comparison test?
This is just all part of that, all right there. That's us trying to figure out what we're comparing it to. So that's actually part of the comparison test.
So with the P being, so if the P were less than 1, oh, we know that is has to be greater than 1 because otherwise it's the divergence, which is
right. If P was less than 1,
series.
it would be divergent, and we still, in this case, would still have to do the limit comparison test because I can't determine if it's greater than or less than that function.
Got it.
So
Professor,
yeah.
that dropdown would offer us the option limit comparison.
Yep, it's going to give you a bunch of different tests, and you just pick the one that matches it.
Okay.
So yeah, in this case, that drop down, you're going to pick limit comparison test.
Are we going to do the actual limit comparison test now?
I guess I could, but for this one, you don't really have to. And I got some other ones that I'm going to do. I'm actually going to do those on the ones that you have to. So
cool.
I'd rather not kill a bunch of time doing it on this one.
Okay.
Honestly, it might work out really quickly. I don't honestly know. I haven't actually tried it. At the end, I can go back and I can do it. See if it's actually that doesn't take that long. So you'll have those notes. But for these problems, like I said, you don't actually have to do it. This one's really just trying to tell you what the tests are.
So this one I think is going to answer my question that what if there are 2 tests that would work? So this one says the ratio test also works. So you want the other test
one. I want the
now
other
in so I'm assuming that in the previous problems there would have been no other way to come to the solution.
Correct. Yes. Or the options. So they don't necessarily give you all of the tests, which also helps. So from their list, you could kind of like, if you had multiple tests that would work, pick the one that's actually in their list because they're not all listed.
Gotcha. Thank you.
No problem. So like this one is blatantly obvious which test we should use because it actually gives you the integral. So yeah, this one is definitely just going to be the integral test. So, and the ratio test would work for this one, as they were saying. So that's why they basically gave you both options. So now the ratio test that's the one with the n+1. So this one, because they actually gave you the integral. Now, I'll tell you why they say it's very easy to do the integral, because if we're looking at this, I would make u the -5x to the 5th. So du would be -25x to the 4th dx. And I already have the x to the 4th in the problem. So I would have the -1/25 integral of e to the u du at that point. So I wouldn't have to actually, since I have that x to the 4th in the beginning of the problem, this integral is very simple to do. So if that x to the 4th wasn't there, I would not do the integral test, because at that point it would be a lot more complicated to do that integral, because I couldn't just do a simple u substitution for it. So that's why if you're looking through chapter 11.7 and they were giving you all the different tests, that's why the integral test is the last one you want to look at, just because a lot of times the integral is not that easy to work with. All right, if you're looking at this original problem, what's the piece in it that would make you say, oh yes, I should use this test? And
The
that is
alternating -1 to the n.
that -1 to the n. As soon as you see that, you're going to do the alternating series test.
So I mean, it's kind of in the wording, since the series is alternating.
Yes.
Are the questions on the test going to be just like this?
Yep. Unfortunately.
Thank you.
Well, I wouldn't say unfortunately. You know what I'm saying?
Well, yes. So some of the ones are going to, the way they word it kind of leads you to the answer. Yes. They don't all lead you to that answer. So some of them you are going to have to actually figure out. But again, my goal is literally to get you to understand, like to try to make sure you can figure out which tests to use. And
Here's the integral. Which test should you use?
yeah,
This is
so it's the nice thing is, well, in my view, the nice thing is there's only a couple of them that actually do that. So there's a few other ones that actually have you do some other stuff. So, but yes, it's not, this test, believe it or not, is not that difficult of a test. The concept was difficult, but the test actually isn't. I've done this test a few different ways, and the other way actually is easier because it literally does a converge or diverge, and it's a 50-50 shot. So unfortunately, doing this online, I don't have as many options as I would if I did it in class. All right, so we've got this one. So this one says, since the series involves a factorial, what was the test that whenever we see a factorial we want to use?
Is that there's ratio and then
We have ratio and we have root.
root.
So this one you're going to want to use the ratio test on. Factorials are ratio test. You want to use the root. So if this was like 5 to the k over k to the k, for example, then we could use the root because we could do the k root on it. So when you have everything able to be raised to a specific, to that a variable power, that's when you want to use the root test. So that would be root test. So in this case, it's the ratio test because the ratios, the factorials are always ratios.
So will it always be that way? If there's a factorial, it will always be the ratio test.
Yeah, because the ratio test works really, really well when you have factorials. Because you end up canceling the majority of amount when you do the k plus 1. So the k factorial disappears and you're left with just the k plus 1 part there. So yeah, the ratio test works well with that one. The ratio test actually is the go-to for a lot of things because it does allow you to break things down and simplify them down, especially if it's in fraction form. If the other tests don't work, typically you try the ratio test. The root test is a little more specific because it only kind of works when you have something raised to the nth power. All right. So this one, they give you, it's related to this geometric series. So we're probably going to do a comparison test. The question is, can we do a regular comparison test or can we do a limit comparison test? So if I have 1 over 2 to the n, which is the same as 1/2 to the nth power. So r is 1/2. Does this converge or diverge when r is 1/2? So for geometric series, is it less than 1? It converges. Well, actually less than the absolute value. So the absolute value of r. So this converges. So I've got to show that 1 over 5 plus 2n is less than 1 over 2 to the n. Is that true?
Yes, because the 5 is always going to make the lower half smaller or bigger than the other side. So that means that the denominator is always going to be bigger than the denominator on the other side.
Correct. So therefore the fraction is smaller. So this is true. So we can just use a comparison test. We don't have to do the limit one. And in this case, that converges. All right, we've now successfully done 6 questions on the test already. Now to the ones we have to actually do some work for. All right, so this one and the next 3 we have to determine if they converge or diverge. So you have to figure out the test to use and then actually do the test to determine if they converge or diverge. So which test do we want to try for this one? So we got n to the 7 minus 1 over n to the 8.
Ratio?
Ratio could work for this one. There's definitely an easy one. The only problem with this one when you're trying to do ratio is when you have, so if we did the ratio for this one, this is what you're going to end up having. So you have n plus 1 to the 7th minus 1 over n plus 1 to the 8th plus 1 times n to the 8th plus 1 over n to the 7th minus 1. The problem is I can't cancel anything out.
Yes, I saw this. You started doing it, realized it.
Yeah. So ratio tests, when you're looking at the ratio test, look for things that only have very specific, like just the variables. So like when we looked at This one right here, notice it was 5K, there was nothing, no addition or subtraction in it, which kind of makes the ratio test a lot harder to deal with. So probably not going to do the ratio test for this. So remember going through on that 11.7. So when you're looking at picking up choices, first off, is this a P series or a geometric series? Looking at it, no. We've got too much other stuff in there. So I know it's neither of those two. The next thing we want to look for is, can I compare it to one of those? So that's the next thing we want to see. Can I compare it to a P series or a geometric series? And in this case, I kind of can. Like if I look at it, I can take and simplify this problem down. So that's A to the n. If I want to do Bn, if I just look at the big parts, I can say, I can do that as 1 over n. Because remember, as we're going further and further out, those -1 and +1s kind of fall apart and aren't really useful as we get higher and higher. So if we just look at that part, I can compare it to 1 over n. Now, does 1 over n converge or diverge?
Diverge.
This is diverge. That is the harmonic series. Also, if you look at it, it's a P series where P equals 1. That means it is not greater than 1. So that also diverged. All right, so we know what diverges. So now we have to say, okay, can I say this? 8 plus 1 is greater than 1 over n. Can I say that? Based on what's there, I don't really know if that's true. So if we're going to do a comparison test, we have to do the limit comparison test. So let's look at that. So I've got n to the 7th minus 1 over n to the 8th plus 1 times n over 1. So this goes to n to the 8th minus n over n to the 8th plus 1. And that limit, if I divide everything by n, sorry, n to the 8th, that's going to go to 1, which is greater than 0. So since it's greater than 0, that means whatever b to the n does, a to the n does. So in this case, a to the n diverges.
Hey, Professor, before we move on there real quick.
Yep.
So when we divide it by n to the 8th, so that obviously becomes a 1, then it's minus n to the -7, right? Because it's on the numerator there. Is that correct?
Wait, repeat what you said. I missed one thing.
Yeah. So when we're when we're dividing the numerator by n to the 8th.
Yep.
Right, so that's 1, and then it becomes 1 minus, and then n to the -7, right?
N to the
Technically
8th
speaking.
over minus n over n to the 8th over n to the 8th over n to the 8th plus 1 over n to the 8th.
Mhm.
So yes, this part right here would just be 1 over n to the 7th.
Okay.
So
Which
it
has-
goes 1 minus 0 over 1 plus 0, which is 1.
Got it. Okay, so this is telling us that it does equal 1, which means
Well, for the limit comparison test, it's just got to be greater than 0. It's got to be greater than 0 and go to an actual value. for the limit comparison test.
Oh, so the first one it told us, so when we did just the comparison test, we knew that it was a harmonic series, we said divergence. But at that point, which info did we still need to figure out at the limit comparison test?
So to do a comparison test, I would need to figure out that the original function, since this diverges, is greater than that in all cases, which it's not. So because I can't determine if it's greater than that, then I have to do the limit comparison test.
If it had been greater than that, because now we know that it's 1, which is, we're saying that it is greater than that, or that they're equal. So
No, so the limit comparison test doesn't, I don't care. This actually you don't need if you're doing the limit comparison test. So when you're doing the limit compare, hold on, let me get to I'll get to the actual piece in a second. I'm just looking for the actual breakdown of the comparison test. So I can just copy and paste it over. Trying to find the, I know what I want, I just gotta actually find it. All right, so when we're looking at the limit comparison test, we've got 2 things we gotta look at. So this is the comparison test. So
Right.
it's gotta be one of those 2 situations. If it does not work in that situation, so in this case, we didn't have that, it didn't work. Because I couldn't tell that a to the n was going to be bigger than that in all situations. So when I did this, that's why there's a question mark there, because I could not determine if that was true or not. So we were not allowed to use the comparison test. So to do the limit comparison test, that doesn't matter in that respect. The limit comparison test just states, as long as we can do the limit, the a to the n over b to the n, and it equals a number. As long as that is a finite number, so it can't be infinity. So as long as it's a number, it doesn't matter what the number is. As long as that number is greater than 0 and a finite number, which 1 is in this situation, then both series either converge or diverge. Since I know my b to the n diverges, therefore a to the n diverges.
got it. So on the comparison test, all we figured out is inconclusive, right? Because
Yeah, because I didn't, it met it, or b to the n divergence, that's true, but we couldn't do the second part of it. That we didn't know.
got it.
So that's why we moved over to the limit comparison test, since we already had something to compare it to.
So we needed to do the limit comparison test. The comparison test first, anyways, right?
Yeah, so when you're doing it, you kind of always start off with that comparison test, like figure out what you're going to compare it to. And then if you can't meet the second criteria of the comparison test, do the limit comparison test.
Got it.
That's why even when we were doing those other ones, when we were trying to figure out which test it was, we had to determine if we could do the comparison test first. And if we couldn't, we chose the limit comparison test as the option.
Thank you.
No problem. All right, this one. Which test would you like to try to use for this one? So it's definitely not a p-series. It's not a geometric series. I actually can't make it either of those, so we're not going to be able to do a comparison test to it.
I see a root there, so I'm tempted to say the root test.
If you have a root, you don't want to do the root test. Because remember, the root test, you want to look at things that are raised to that. So you're looking at something. So if this problem was raised to the nth power, then the root test. The root test doesn't help you get rid of a root. It actually adds a root to the problem.
Oh, so you wouldn't look at the square root of something as being raised to the 1/2 power?
Yeah, you could, but remember, so the root test, it's the nth root. So you're actually not getting rid of a half, you're actually getting rid of the nth power. That actually, so the root test is actually, you know what, let me find it, I'll get it. Since I already have that one. Let's try the- So this is the root test. Notice how it's the nth root, not the square root, not the 1/2 power root, whatever. So even if this was raised to the 1/2 power, if the whole thing was raised to the 1/2 power, the root test is still an nth root. It's not a 1/2 root or square root or anything. That nth actually is not a variable you can plug a number in for. That way.
All
It
right,
actually is always the nth root.
so does that mean that we want to use the integral test for this one?
Yeah, this one actually is the integral test. This one does end up coming down to the integral test. So let's refresh our memory on what the integral test is. So this is my integral test. So we need to know that it's continuous, positive, and decreasing. So the first thing is this continuous? Since we're starting off at n equals 7, I'm going to say yes, that's most likely continuous. Because I can't think of a value I'm going to plug in for ln that's not going to make that work if we're starting off at 7. Is it positive? Yes, there's no value in that that's going to give me a negative number. Last question is it decreasing? You could sit here and go through and do out the derivative and stuff for it. This one, the bottom is definitely going to be getting bigger for it since the top doesn't really change. This one's decreasing. So we can assume those three things and not actually have to test for them. So now we're just doing the integral for it. So we're taking the integral, doing it from 1 to infinity of 1 over n ln of 6n.
Is it technically 7 to infinity?
Huh? Oh, yeah, it would be 7 to infinity. Good catch. I'm just always used to doing them from 1. All right. So in this case, what do I want to use as my u? Let's try a u substitution for it. So what do I want to
That nasty square root there.
Yeah, let's just do what's underneath the square root. So yeah, let's just do the ln of 6x.
6x.
So if we do du of that, this ends up coming out to be actually just 1 over x.
Wait, could you explain that real quick? Sorry. Where does the 6 go away? Why does it go away?
So it's actually, I don't think it does. They have a mistake in the answer book. 6 actually stays. I'm looking at it, I'm like, because we have to do the chain rule. So you do the derivative of the inside, which is 6. Oh, that's why. They just didn't write it. So you do the derivative of the inside, which is 6, right? And then you do the derivative of the ln, assuming the piece inside, which would be 1 over 6x, which is just 1 over x. That's why.
You said you do the, oh, I see, I see.
The chain rule is the derivative of the 6x, which is 6. And then the derivative of the ln if the 6x was just there. So it's ln of x, basically, which is 1 over whatever's inside, which is 6x. So the 6's cancel each other out. That's why you just get the 1 over x. And the reason why we can do this as a integral test is because I have in the problem the 1 over x. So this problem now just becomes integral of 7 to infinity of 1 over the square root of u du. Which ends up becoming 2u to the 1/2 plus b. Although I don't even care about the c because I'm going to plug numbers into it anyway. So this is 2 ln of 6x evaluated from 7 to infinity. So if we plug in the infinity, I've got 2 ln of infinity basically minus 2 ln of 42, which this most definitely goes to infinity. So since my integral diverges, we're in that situation, so that function diverges. Any questions with that one? All right. Next one. We've got this one. What do we want to try with this one?
Wasn't there like a specific rule for when we involve sine?
I don't think there wasn't really a specific rule, but there's definitely a nice way to do it. So we're actually going to use like the absolute convergence. So the reason why we're going to look at this, so sine and sine, cosine, tangent, they don't alternate, but they go between positives and negatives. So you have both values in there. So absolutely convergent, basically, if I look at the absolute value of it, so I take away that alternating piece in there. If that's convergent, then I know the whole thing is convergent. So that makes my life a little bit easier. So in sine, in your trig functions kind of work well with that. So if we look at the absolute value of sine 7n over 1 plus 6 to the n, if I look at this, I can come up with something that compares to it. So this is when we're looking at the trig functions, I was going to say, okay, I can basically take the top and just say, well, the top is going to be 1. And I know that this is always, or the sine 7n is always going to be less than the 1, because sine goes between the 1 or negative 1 and positive 1. So in this case, it goes between 0 and 1 because we're looking at the absolute value of it.
Oh, so we assume that the top goes to 1 because it will always be positive?
Well, I'm not assuming the top goes to 1. I'm saying that the top is always less than 1.
Less or equal to.
Yeah, because it could actually equal 1. So, and that's fine, because when we're comparing things, less than or equal works, as long as it's less than or greater than always, as long as it doesn't switch back and forth. So that's where we're looking at. I'm basically saying that sine of 7n is going to be less than or equal to 1 in this situation. Because we're basically going to look at a comparison for it. And this one, I can simplify down to 1 over 6n, which is 1/6 to the nth power.
How do
So,
how do we get rid of that 1 on the denominator? Just over time, we're just saying it doesn't matter as it gets to 30.
well, actually, it's not equal. It's less than.
Right.
Again, I'm just saying it's less than at that point. It wasn't equal. That's equal. So so basically this is going to be, so when I'm looking at it, the absolute value of sine 7n 1 plus 6n is less than or equal to 1 over 6 to the nth by the transitive property there. Now, does this converge or diverge? The 1 over 6 to the nth.
If it's less than 1, it converges.
Correct. This is a geometric series. So my R equals 1/6, which is less than 1. So this side converges. And since it's less than, that side converges. So we don't need to do the limit comparison test or anything else like that because I know it's less than, which is the definition of the comparison test.
So we're effectively, so we're just comparing it to the fact that we know this geometric series converges. So we're saying because it's less than it, it also converges. If it was greater than it, we would not be able to make that. We would, would we be able to make that claim?
No, because it would have been greater than. Remember this. So since b to the n is convergent and a to the n is always less than bn, it's also convergent. If bn was divergent, it would have had to been a to the n is greater than b to the n.
And when those are not the case, what's the thing that we're going to?
If we don't know that second part, I have to do the limit comparison test.
And that at the limit comparison test level, we're just making sure that it's not infinity.
Correct. And it goes to a finite number that's greater than 0.
If it goes to a negative number,
then it doesn't work.
What would we do then?
You have to try a different test. However, if we're thinking logically here, if I'm doing a limit comparison test and I'm comparing two functions that, based on the definition above it, all have positive terms, they can never go it can never go to a negative number. So we would not do the comparison test to begin with if we were going to get negative numbers. We would do the alternating series test at that point. Or we would do the absolute comparison test, the absolute convergent test, which is what we just did, and eliminate the negative numbers to begin with.
So when C is not a finite number,
If it goes to infinity, then it fails this test.
where does that leave us?
We'd have to try a different test.
And it really depends on the function, I guess.
Yeah, and then you'd have to either do the integral test or a root test or a ratio test. It really just depends on which function, which test, or what the problem is at that point. The key is, though, if you're choosing the test correctly at the beginning, you won't run into that situation.
So I noticed that on the practice for this one, it talks about writing out our steps.
Right. So you're just going to show me all your work.
Yep.
So actually, yeah. So basically what this problem is going to do for the ones when you're doing it on WebAssign, it's going to give you steps that are going to have you walk through the process. So this problem right here, what it's going to give you is it's going to tell you it's going to give you the information that you're doing. So like, for example, this one says, we're going to use the ratio test to determine it. So by doing that, it's going to have you, it basically has you walk through the ratio test. So it gives you this part. It says the limit as n equals to infinity of an plus 1 over an equals. I'm literally writing what they actually have for this one, so you can see how it's going to actually look. Equals. So it wants to know what would go in that box. Is what it's asking. So if you look at how this problem up here is, if we were to flip this all over, so we have x minus 12 and then times x minus 12 to the n. And then we have the x minus 12 to the n on the bottom. So those two are going to cancel out.
So we put x minus 12 in the box.
So right, in that box will be x minus 12. Because they already have, so this part right here is that part. And that part is that part. So they already have the other pieces. So they're looking for in there the x minus 12. Okay. So the next part of this one. They go, what's the limit of, as n goes to infinity, of the n squared plus 1 over n squared plus 2n plus 2. So if we take the whole thing, we divide everything by n squared, I get 1 plus 0 over 1 plus 0 plus 0, which equals what?
Well, don't we still have to multiply that by the x
Yes.
minus 12?
Yes, but this, so the way, I'm literally working it out the way they're showing it. So they're, because the next piece is going to say, okay, this is the limit, then it's the x minus 12 is left. So the question was, what does this limit go to of that part? So then they go, the limit as n goes to infinity of the x minus 12 n squared plus 1 over 2n plus 2 goes to x minus 12. So which test were we using?
The ratio test?
Right. So the ratio test converges when?
If L is less than 1, it converges.
Correct. So we know that x minus 5 or x minus 12 has to be less than 1.
Okay.
Now that we got that, we can come back and we're going to find out the final answer. What's the radius of convergence and what's the interval of convergence? So my radius in this case, since there's nothing over there, is 1. Because remember, it's the number in front of the x is basically ends up giving you your radius. So my interval, so radius is 1. And now my interval, I have -1 is less than x minus 12 is less than 1. So add the 12 to both sides. So I got 11 is less than x is less than 13. So my interval right now is 11 to 13.
Wouldn't that be less than or greater than equal to as well?
No. Because remember, what's the ratio test? If it equals 1, we have to determine, we have to look at it as something else.
That's the interval there, right? How do we, so that's I? What's the radius?
The radius is how far from the middle out. So you could actually do this as 2 separate ways. Like you can find the radius, find the interval first, and then find the radius.
So if we had set at x equal to 11 or x equal to 13, it would not converge?
I don't know. I haven't done that yet. That's the next step.
Oh,
We still have to do that part. That's next step. So, right, the next thing we have to do is we have to actually determine if they're going to converge at the endpoints. So I've got 11 less than x is less than 13. So we got to plug in those numbers and see what happens. So if x is 11, I have -1 to the nth power over n squared plus 1. And in that case, I'm going to use the alternating series test for it. And for that, I have to know that it's decreasing. So, and the limit. So let's do the limit first. So I have the limit as n goes to infinity of 1 over n squared plus 1. And that goes to 0. So that's good. And then bn plus 1 is less than or equal to bn. And yes, that's going to be true because if the denominator is getting bigger, therefore it's going to be less. So that would also be true. So this converges at 11. Now we do the 13. So I have 1 over n squared plus 1. So to do this one, we're going to have to, we can do a comparison test for this one. Because it looks like a p-series. So I can compare this to 1 over n squared. So that's the p-series where it's 2, which is greater than 1, so that converges. So now I just got to show that 1 over n squared plus 1 is less than or equal to 1 over n squared, which that's also true. So this also converges. So my final interval for this one is 11, 13 with the brackets after we tested the two cases. And they actually have you walk through those that whole process for this one. Questions with that one? I will tell you, when you're going through and doing it on WebAssign, if you're trying to go on and it's not letting you go on, you got one of two possibilities. One, you did something wrong, or two, you're putting in the answer, like you're actually typing it in incorrectly, like how they want it written. So go back and look at it before you go on. All right. Next one. 2 more to go.
Why is a radius of convergence or interval of convergence useful?
So your interval of convergence basically, so now remember we have, when we're looking at these are power series. So we have an actual variable in it that is not necessarily part of the problem. So when you're looking at this series, unlike all the other ones that we did, those series were very specific. It was one series. This is actually a family of series because it's every possible value for X that would work. So when we're looking at the convergence, this series converges and diverges. It just depends on what the variable is going to be. Depends on what X is going to be. So by giving you the interval, we know this family of functions, this power series or this family of functions is going to converge only when X is between 11 and 13. So the interval is more important than necessarily the radius. The radius is just another way to look at it to see how wide that actual interval is going to be. That's why I said you can find your interval first and then come up with your radius. So the reason, so when we're looking at these series, we're looking for radius of convergence or intervals. The ratio test is one of the major ones we're going to use to do these, just because we have the ability to actually determine where it's convergent or not. So you can probably notice that pretty much all the ones that we did when we did it out, we did the ratio test for it. And then when we were testing the endpoints, we had to use some of the other tests for it. So we're going to do the ratio test for this one again. So an is 10 to the n, x to the n over n to the 4. If the bottom was n to the nth power, you could have actually used the root test for this one. But it says it's n to the 4th, we have to use the ratio test. So we're doing the limit as n goes to infinity of, we have 10 to the n plus 1, x to the n plus 1 over n plus 1 to the 4th times n to the 4th over 10 to the n x to the n. So I can reduce these down. I'm going to get 10 absolute value of x times n to the 4th over n plus 1. Actually, let me just put them all together to the 4th. So this goes to, because that's the n over n plus 1. We divided all that out. That ends up going to 1. So this goes to just 10 absolute value of x. Questions with that part?
There's a general idea there is that one won't matter as it goes to infinity, so it's just 1 over 1 to the 4th, or infinity over infinity to the 4th.
No, it's actually 1 over, it's because you divide them all by n, so you're going to get 1 over 1.
Oh, right.
So it's just 1 to the 4th. There's just
That should
one.
always be the first step in our mind is to divide it all by the biggest factor, right?
Yes, always,
Normalize it.
whenever you're doing the limits, always divide by the biggest factor to get rid of them. Because once you have division, then we have the fractions go to 0, which helps you out. All right, so I've got 10 absolute value of x. That has to be less than 1. So then I have the absolute value of x has to be less than 1/10. That is your interval. Oh, no, sorry, not your interval, your radius. So my radius in this case is 1/10. So I've got negative 1/10 x to 1/10.
How, what does it mean that it is less than 1 here? Like, what if it were greater than 1?
Remember the ratio test. The ratio test.
Convergence, right? Less than 1 equals is convergence, greater than 1 is divergence.
I know I had it. Where did I delete it? I swore I had it. I must have deleted it. Yeah. So, I had the root test and I deleted the root test. Yeah. So less than 1 is convergence, greater than 1 is divergence, and equal 1 we don't know. So since we're looking for the radius of convergence, that's why we're setting it less than 0 or less than 1.
And if it's unknown or they're equal to 1, then we.
That's why when we're doing this one, we set it less than 1, but then we test the endpoints because that's where it would be equal to 1 to determine if they converge or diverge.
So that's
And
what the next step is.
That's the next step. So we've got copy this over. So we know it's from we got negative 1/10 to 1/10. So we're going to plug those in. So let's say x is negative 1/10. I'm going to have negative 1 to the nth power over n to the 4. And that one I'm going to do the alternating series test. The limit as n goes to infinity of 1 over n to the 4th goes to 0. And 1 over 10 plus 1 to the 4th is definitely less than 1 over n to the 4th. So that also checks out. So this converges. So I know.
Slow down on that one, Professor.
Huh?
So when you put in the 1/10 to the x, right?
Yep.
Or the negative 1/10. So we're keeping the negative, right? Which means alternating series.
Yep. That's that. That's I got the negative 1 if that's what that part you were asking.
So we're just not dealing with the 10 to the n part.
You did. The 10s cancel each other out. You have 10 times negative 1/10, which is negative 1.
Oh, okay, got it.
And actually, the same thing is going to happen when I plug in the 1/10. It's just not going to be negative. It's just going to be 1. So it's just 1 over n to the 4th, which that's a p series. So p is 4, which is greater than 1. So converges. So it's also there. So my interval is negative 1/10 to 1/10. And the WebAssign wants it written in that format.
I'm sorry, so for the negative 1/10, as n approaches infinity, when we're looking at that second part that you wrote there, first time you wrote converges, to the right of that, right there. So as n approaches infinity, wouldn't that grow infinitely large on the bottom?
Right. Which is fine. The bottom was going to 0. That's what we're
Oh,
doing over
because-
here. The alternating series test looks at that part. And one of the two pieces is it has to go to 0.
Gotcha.
That goes to 0.
But the fact that it's raised to the nth power on the top doesn't
That's
matter
a-
for the
so-
alternating series test?
No, that actually is the definition of the alternating series. That's why we can do the alternating series test, is because I have the -1 to the nth power. If I didn't have the -1 to the nth power, like in this one here, I don't have that. That's why I can't do the alternating series test in the second part, because I don't have that -1 to the nth power.
The first stipulation of the alternating series test is that it needs to go to 0 and then it needs to decrease.
Well, the alternate, yes, it has to decrease, and the limit of that has to go to 0. That's why the alternating series test is so nice, and that's why I always do that limit part first, because if it fails that limit part, it passes the test for divergence, and we're done.
So if it fails, meaning it
If this does not go to 0,
it's just gonna diverge.
correct.
And that's only for alternating series, though, right? Because if it's not that every function that goes to anything but 0, like converges, or anything that other than 0 diverges, or is that
The test for divergence says if we just look at the limit of the sequence of the series, which is basically what I just did over here, if it goes to anything other than 0, it diverges. That's for any series. That's what the test for divergence says.
okay?
So, because in essence, remember, we're looking 1/n⁴ is what I'm adding. Because this is a series, so I'm adding up all those terms. If the last term in the series that I'm adding isn't 0, it's always going to get bigger. Therefore, it fails. It doesn't converge, it diverges. The last term in the sequence, as the limit goes to infinity, has to be 0. Otherwise, it's guaranteed to diverge. The opposite of that isn't true, though. If it goes to 0, I don't know it converges. And that's why we have to do the other tests.
I see. So we're saying because it converges on both, then it's closed brackets or not parentheses.
Correct, yes. It's equal because it converges on both ends. All right. All right, last one. So this one, they're giving you the function, and we want the power series. So we're going the other direction. So remember, in this one, we're using the geometric series, the 1/1 minus r equals the summation of n to 0 of infinity of a r to the n. So we need to convert it into that format. So we need to take 1/4 plus x and convert it to the piece that I can get 1/1 minus r. So the first thing I'm gonna do, I'm gonna pull out a 4. So I get 1 plus x over 4. And then I'm gonna pull out the negative sign there. So I get 1 minus negative x over 4. So now this side right here is 1/4 times 1 over 1 minus negative x over 4. So I can change this side to the 1/4 out in front, and then negative x over 4 to the nth power. Okay? That part makes sense? So I have 1 over 4 n equals 0 to infinity of negative 1 to the nth x over 4 to the nth. So now my ratio, remember, so since this is a geometric series, it's the absolute value of r is less than 1. So in this case, I have x over 4. The absolute value of that is less than 1. So I have negative 1 is less than x over 4 is less than 1. So I got negative 4 to 4. So my interval is negative 4 to 4. Why
So
don't
for
I
the
have to
first-
test? Oh, go ahead.
Sorry, for the first part of that question, find a power series representation. That was that first part where we ended up getting the 1/4, 1 over 1 minus negative x over the over 4 equals 1/4 sigma, all that rest of that junk.
Yeah, that's the power series right there.
Is it important that we recognize that it's an alternating series?
Not really in this case. It's just there, again, WebAssign wants you to write it a very specific way, so that's why I pulled up the -1, because that's how they want you to write it.
Okay, so quick question. Okay. So R, because it's a geometric series, if it's less than 1, it's convergent, right?
Correct.
So what R is just, you're talking about the AR to the N, the geometric series
Yeah, R is the ratio.
is the
which in this
ratio.
case is x over 4.
So how do we know that x over 4 is less than 1? That's kind of where I'm missing
Because
that.
that's the ratio. So we've got this series right here, which we know which is a geometric series, because we did all the work basically making a geometric series.
Okay.
So by the definition of a geometric series, the ratio is less than, it converges when the ratio is less than 1. In this problem, the ratio is x over 4.
That's what I'm saying. I understand that if the ratio is less than 1, it converges. How do we know that x over minus over 4 is less than 1?
We don't. We're trying to figure out where this converges. X over 4 can be anything. We're trying to determine where this converges. We're trying to find the interval of convergence. So we're saying when x over 4 is less than 1, it converges.
Got it. So now we're saying it does it converges between -4 and 4,
Correct.
and now we got to test the endpoints.
No. That was actually going to be my next question. Why don't we have to test the endpoints? In a ratio test, 1 is inconclusive. So we have to test the endpoints. In a geometric series, 1 is divergent. And we know it's divergent. The ratio is only convergent when x is less, or when r is less than 1. So when r is equal to 1 or when r is greater than 1, it is divergent. So we don't have to test the endpoints because we know it's divergent at those 2 points. Okay, so that actually is my interval, and I'm done with that.
Are you doing after hours today, Professor?
I can do a little bit. I could actually also do it on Monday if you want. If you want to actually practice it before, and then we can, I can do office hours on Monday if you want. It's up to you.
I mean, I'll take, if you have 10 or 15, I'll take them here.
Okay. Yeah.
And
I
on
will.
Monday. I need all the help I can get.
Yeah, I'll take office hours Monday.
Okay. Same time, 5 o'clock works.
Yeah.
All right.
Professor,
Yep.
will you be available early on Tuesday?
Oh yeah. Actually, I'm on spring break next week. so yes, I'll be on at 4 o'clock to start the test early.
Okay, I find myself using most of that extra time each time.
That is fine. I will definitely be on early for Tuesday's test.
Thank you.
Not a problem. All right. If you're, let me stop this.